All right, welcome back everyone, or welcome to those of you who didn't attend the first webinar with Charles Gullidge. Again, I'm Ray Burke, Executive Director of AABC. And before we get going with our second technical webinar today, we're going to take a moment for a brief message from AABC industry partner and sponsor of this session today, Performing Instruments, and we'll be right back to kick off the next session.
Could sell more tab. Our variable hood cover installs in seconds. Saves time and makes you money. It's true. Personalized hoods sell more tab.
All right, and thank you very much to Performing Instruments for their support. A few very quick Zoom notes. Again, if you have questions for the speaker, please use the Q&A specific section at the bottom of your Zoom window to submit those to us, and no need to wait until the end. Just type those in whenever they occur to you. For the chat, if you have any technical difficulties, hopefully you won't, but if you do, put them there. Our technical specialists will help as best they can. So for our second webinar for the AABC virtual annual meeting, we have Tom Smith, President and CEO of 3Flow. Mr. Smith is a degreed mechanical engineer with a master's in industrial hygiene. He's worked for more than 30 years helping facilities provide safe, efficient, and sustainable labs and critical workspaces. He's also been active in contributing his time to the industry, and he's been a frequent and well-received speaker at AABC meetings over the years. Tom's presentation today, New Methods to Verify Proper Functioning of Modern Fume Hood Systems. We'll discuss proper techniques for measuring face velocity, evaluating variable air volume, flow response, and diagnosing problems affecting fume hood containment performance, as well as new methods under development to simplify and reduce the costs of conducting fume hood tracer gas tests. Tom, take it away.
Okay, thanks, Ray. And let me start by thanking everyone for their time to attend today. I really appreciate it. Also, thanks to AABC for the opportunity. I've had a long relationship with AABC. It's always great to work with professionals that really understand the physics of air. So today we're going to talk about some methods that have been developed to really address modern fume hood systems. So we're going to talk about what is a modern airflow system. How is it configured? How does it operate? Why do we install them? What do we hope to benefit from installing a modern airflow system? We're going to talk about some of the fume hood test methods. And then we're also going to move on and look at not just the fume hood, but the lab environment and the system and how the system operates to modulate flow in response to the sash opening and closing on a hood, or varying the volume through the fume hood. And then we'll talk about the benefits of a top-down approach and how to integrate all of the different stakeholder groups from tab and commissioning and fume hood certification into a more comprehensive, more effective process for evaluating laboratory hood systems. So looking into laboratories, we find out that people are working with all kinds of different materials, and they do this on purpose to develop new and innovative technologies. And so the whole building is in fact built to promote research success. And so the laboratory has to meet the needs of the occupants to provide a safe environment, but an environment that's conducive to good science. And so that means temperature control, it means proper indoor air quality, and all of these factors are going to be associated with the HVAC and how it operates. But labs can be dangerous, and as we're working on these systems, we have to remember that the things that are going on in the labs are going to be transported through the duct. And there's a possibility of having an existence of chemical hazards or biological materials or radiological materials, and there can be physical hazards that can also retain in the ductwork. flammable materials, things like perchloric acid can form perchlorates and become very unstable. And these are things that not only can affect the researchers, but it can affect those people that are working on or around the systems. And so we want to really understand that risk profile and how do we protect ourselves when we're verifying the proper operation of the systems. So look at it, let's take a look at a system. We're going to build up a system. So we start down in the labs themselves. And so when we have a laboratory configuration, we can add some laboratory hoods, not just fume hoods, but there might be other types of local exhaust ventilation devices. And we need to exhaust that material from the hoods. And so we can have a single hood, single fan, or a manifolded exhaust system. And let's add some ability to modulate flow or to distribute the flow properly. So we have an exhaust system that enables us to achieve the appropriate flow through each of the devices. But because we're exhausting air out of the building, we have to supply air back to the building. And so we also have to distribute that flow properly. So these two systems can be looked at as independent, but they're not mutually exclusive in that they work together to provide the conditions within the space that are necessary to support the science and create a safe and comfortable work environment. But these systems start to become more complex when we add various other types of controls and systems. So we can have energy recovery. That's a requirement in certain portions of the country now. We can add our building automation system, which is an array of sensors and controllers and actuators. All of these parts and pieces have to function properly and be working in tandem in order for us to deliver the appropriate amount of flow and exhaust it from these spaces. And then we can add additional systems now, occupancy sensing and demand control ventilation. These systems add additional complexities that have to be confirmed that they're operating properly so that we achieve the objectives. And then we add the most difficult component, which is the humans. The people can do some crazy stuff in the labs, and they're very innovative people. And so we're constantly trying to make sure that we're meeting their needs, which we call the demand for ventilation. So let's get some airflow through the building. And as we expect a system to modulate flow, as they open and close the sashes or the labs are going occupied or unoccupied, then we expect that the flow is going to modulate from the hoods and translate all the way up to the exhaust systems. Now, if this airflow is modulating through the exhaust system, we have to also anticipate that the air supply is going to modulate in tandem, and so that they're going to be working in a lead lag type of an arrangement. But in order for us to ensure proper air balance for the building, there can't be a wide variation between the exhaust and supply. We want them to match, and they need to modulate in tandem in order to achieve that proper balance over the whole range of operation. So one of the big questions becomes, if we're going to save energy, if we move the flow through the hood, we modulate flow, how does that translate to a reduction in flow through the systems? What's that VAV sensitivity that modulates flow? Well, we also know that the energy consumption is mainly associated with HVAC operation. So how much flow is going through the building and how much it's being conditioned. And so that conditioning and transport of the flow are the major energy components. And so when we look at the major factors driving energy consumption, it's going to be HVAC, number one, 45 to 85% of the energy is associated with HVAC. We have plug load, maybe that's 25 to 30%. And we have lights, which may be 5 to 10%. And then there are some other miscellaneous factors that associate with energy consumption. But over time, we want to understand what these metrics are. How much flow is going through the building from minimum to maximum, and what are the average metrics for flow, energy consumption, and so forth. So if we understand occupancy, operation, and energy consumption, we should have the three factors that correlate to give us an understanding of how the system operates at any given time. So fume hoods and laboratories are designed to control exposure to airborne hazards and simultaneously condition the space. And so we want to rely on the hoods to provide source capture, and where necessary, we rely on the lab for secondary containment. And so we need to then also rely on the appropriate amount of dilution and contaminant removal. So the supply and the exhaust work in tandem to make sure that we're providing proper safety as well as appropriate conditioning of the space. So we need to then look at how do we verify that it's going to operate properly and perform to meet these objectives over the whole range of operating modes, which might be Sash closed, full cooling, full heating, occupied, unoccupied operation. As these systems get more complex, the range of operating modes can vary. So in 1991, OSHA passed the 29 CFR 1910.1450, which is the lab standard, and it requires all facilities to have a chemical hygiene plan. It requires facilities to ensure the proper functioning of fume hoods and ventilation systems, and it requires proper testing and maintenance of fume hoods and other protective equipment. So it's a law. It's not an option for facilities. They must ensure the proper functioning of fume hoods. They must protect their people from overexposure. So it's an actual requirement. So we're going to focus on proper testing. So recognizing that fume hoods are installed for one singular purpose, and that's to protect people. They are the primary safety device used in laboratories to protect people. So we have to ensure that not only are they functioning properly, but they're operating at the appropriate face velocity, but they're actually protecting people from exposure. So we have to move beyond just face velocity testing. We have to evaluate how is it functioning from a performance standpoint to protect people from exposure. So that job of the hood is to contain, capture, and remove airborne hazards. But hoods are fairly complicated. They're what's called a complex hood, a compound hood that has an opening based on the sash position. Vertical sashes go up and down. Horizontal sashes go left and right. But this happens to be a vertical sash. And we know then the simple math that velocity times the area of the opening equals the exhaust flow. And those are values that we're all very familiar with. But here's the question. What is the safe average face velocity? So you might be answering that question yourselves. Let me give you a little bit of help. Is it 40 feet per minute or 60 feet per minute or 100 feet per minute? What's the safe average face velocity? Well, as it turns out, there is no safe average face velocity. The face velocity has to be appropriate to protect the person. And we don't know who's going to be using the hood. We don't know what materials and equipment are being used inside the hood. So how can we arbitrarily pick out a face velocity that's going to maintain adequate containment with respect to all the factors that influence performance? So we have to make sure that when the face velocity is specified, we have the appropriate amount of flow to deliver that face velocity, but we can't say it's safe. We can only say it's operating at a particular face velocity. So there is no face velocity that is safe. There are many other factors that influence protection. So the ASHRAE 110 test was developed to evaluate hood performance, and it's divided into two basic sections. The first section is the definition of operational conditions. Under what conditions are the hoods operating? And under that set of operating conditions, how well does it maintain containment performance? And so when we look at factors such as face velocity and the air velocities in the room around the hood, or how the VAV system's responding and its stability of flow, those are evaluation of operational conditions. And under that set of conditions, we want to look, does it contain visually during a qualitative airflow visualization or a smoke test? Or can we quantitatively evaluate containment? We place an ejector inside the hood, we generate a tracer gas, we measure breathing zone concentrations and detect those with a meter that allows us to measure down to 10 parts per billion. On a visual limitation for smoke testing, you can only see about 100 parts per million. So the hood there may be escape from the hood, you just don't see it. But with the quantitative test, we can actually measure it. And these tests can be conducted at the manufacturer as manufactured. That's testing the design of the hood, as installed, after it's installed, before people use the hood, and then finally during commissioning, and then finally as used based on risk associated with the application. So 3Flow, we've conducted over 40,000 tests on hoods throughout North America. And when we look at the data retrospectively, we see about 15 to 30% of hoods fail to provide adequate containment in accordance with the ANSI Z9.5 standard. And those factors that influence the ability to contain are associated with the design of the hood. Does it have the appropriate aerodynamic qualities? We look at the lab design and operation of the system to make sure that they're proper and appropriate for containment. And then finally, work practices. So lab design and system operation by far indicate the greatest potential for problems. And so we really have to focus on how do we ensure that the systems are operating properly and are conducive to proper hood containment. So we look into the hood and we ask the question, what's missing from this fume hood? Now, each of the components of a hood are very important. The vertical sash has to go up and down. Horizontal sashes go left and right. We need aerodynamic entries, but in this particular case, we're missing the all-important airfoil sill. Without an airfoil sill, the airflow will go into a vortex right along the work surface and enable people to be exposed when they access the hood. Other factors we see are, this is a VAV hood. When the flow is too low, we see that it's not adequate to transport the materials out of the hood and through the ductwork. And so we can get materials raining back into the hood. So if you see this type of indicator, that says that we don't have adequate minimum flow to transport the materials out of the hood. So processes that can generate high volumes of effluent, we need to make sure we have a sufficient minimum flow in order to maintain containment, as well as dilute and remove the materials from the system. Another problem, can we certify these hoods? If you look at this hood on the left, it says, please keep clean. But it's so cluttered with materials, how would you possibly test it? But yet there's a sticker on the hood. And then we go over here, you can't close the sashes. There's stuff protruding out of the front of the sash. And so again, we would be reluctant to do any type of testing on these hoods because they're just not being used appropriately. So the answer to this question is no. You should not certify these hoods because then you would be verifying that they operate correctly, and that's not the intent of the test. So now we also look into a lab. Now, if you look into this space, what do we see? We got a hood over here on the left. We've got supply diffusers. They look like good diffusers, but if we count the ceiling tiles, 2x2 diffusers, or 2x2 tiles, we only see that's about 2.5, maybe 3 feet from the hood. Diffusers should be at least 5 feet from the hood. If they're too close, we're going to get cross drafts that create turbulence, and that can also short circuit air directly to the hood, so we're not getting the utility out of that heated and cooled air into the lab space. It's being short circuited and possibly causing problems with hood containment. So that's another factor we really need to look at, and diffuser should be at least 5 feet from the plane of the hood. Now, we spend a lot of time up on the roof, and when we look at exhaust stacks, if you want to look at this particular system, there's a whole bunch of problems with this. Obviously, we have a person on the roof, and so when we look at this system, we notice that, well, there's improper duct configuration. It's not a uniform elbow going into the fan, so we're going to have some system effect factors. And then we have a low stack height, and then we have an air intake that could be downwind. So there'd be possibility of exposure to people working on the roof, as well as reentrainment of the materials back into the system. This is a very common problem. We see about 5% of systems fail due to inadequate discharge of the exhaust from the building. And so there's a whole bunch of problems associated with that. People have been exposed and suffered brain tumors and miscarriages and birth defects and liver damage and respiratory problems, all from this condition of low stack height and reentrainment. Very insidious problem. We need to make sure we've got those stacks at least 10 feet above the highest structure on the roof with sufficient discharge velocity to prevent people from being exposed or being reentrained back into the building. Now you look at this roof and you see these induction type fans, and there's a lot of them. Kind of reminds me of the terracotta soldiers, but when I look at this, it all looks pretty good from this perspective. However, if we change our viewpoint and walk over here and look to our right, we find out that these stacks are actually right next to the air intakes. And so when they started up this system and people began using chemicals, they wondered why were they smelling materials inside the building? Why were they getting headaches and other things that were occurring from an adverse health perspective? So we need to look at the system holistically. That's why we're going to take a top-down approach. If we expect the systems to modulate flow and we want to look at how do we minimize energy consumption, we should make sure that the systems are working properly first, then look at the lab environment, and finally the fume hood tests. So let's start at the bottom and work our way up. With the fume hood tests, we have a vertical sash opening, goes up and down, and our horizontal sashes go left and right. Those are different operational configurations, so every hood that has multiple or combination sashes has to be tested in both configurations. We need to evaluate what are the appropriate operating specifications. Q equals VA, velocity times area equals exhaust flow. But that's not the only question. We need to know what is the sash opening configuration. What is the average face velocity required for proper operation? Traditional hoods typically require 100 feet per minute, but a brand new high performance hood could go down as low as 60 feet per minute. So that's another question. What kind of hood do you have? And then if you have a VAV hood, how low can you go on the flow? When that sash is closed, how can we reduce that flow and how low can we go before it becomes a problem? We got to maintain enough containment, and we have to dilute those materials, and we have to transport them out of the system. So the minimum flow becomes very, very critical. So we have a process, and this was developed with the US EPA to put it into a standard operating procedure. It's based on ASHRAE 110, but we start with inspection of the hood, cross draft velocity measurement, face velocity, VAV response, then our performance test. So for this presentation, I'm going to focus on VAV response, the airflow visualization, and tracer gas containment, because I think everyone here listening and watching knows how to do the cross draft and velocity tests very, very well. So VAV controls come in lots of different types of equipment, different configurations. We have sash sensing, we have through the wall velocity sensing, we've got occupancy sensing, we've got combinations of these different components. That makes systems very complicated with a lot of different potential modes of operation that need to be challenged and confirmed that they work properly. So the VAV system is relied upon to modulate flow from sash open to sash closed. So in the sash open, we need to know that minimum flow required. And then when the sash is closed, how low can we go? What's that minimum? How do we determine that we're at the appropriate minimum flow? Of course, as balancers, we would do a pitot traverse in the exhaust duct and confirm it. But what if we can't? How do we look inside the hood and determine it from in front of the hood what the minimum flow is through that fume hood opening? And then how do we calibrate the monitors? We need to make sure that we've got a good calibration in order to get reliable data, and that information is going to be shared with the building automation system. So the accuracy and precision of our measurements here are very critical because they drive the operation of the system. So we can look at different types of monitors, flow, velocity, and pressure. All fume hoods should have a monitor to alert the user to a low flow condition or an improper operating mode. And then we have different control types, as I mentioned, through the wall, sash position, occupancy. In some cases, we may even have manual. That should be discouraged. And then we have different operating modes, two-state control, full VAV, VAV hybrid. So you could have a sash position controller that modulates flow based on sash position, coupled with a zone occupancy sensor. So now you have a different mode of operation. When someone walks away from the hood, it goes to a lower flow. Who challenges that? How do we make sure that that flow actually modulates as we expect? So looking at this evaluation, we could measure the flow in the duct. We could take the flow off the flow sensor if there was one equipped on the VAV, but oftentimes it's very hard to gain access to the duct or the controls. But we find out that the velocity through the slot and the baffle is equivalent, or it's a proportional to the flow through the duct. So the velocity here, Q equals VA, is proportional to the exhaust flow. So if we can measure the velocity in this slot, we can then use that to correlate the flow and then determine as we raise and lower the sash, how that's modulating flow. So here's an example. We'll show a little video here. And as we're recording the data. We've got the sash closed, we've got our probe in the baffle slot, and we're watching the velocity. And I'll just move it over here a little bit until we open the sash, and now we see the flow increasing to where it's coming up to a value. And then we go through 3 cycles of this. We're going to close the sash. And when we go through and close the sash, we'll see the flow go down, and 3 cycles of opening and closing. So as we move along, I'm speeding it up a little bit, obviously, because you can tell I don't move that fast. But this allows us to look at the modulation of flow. We do 3 cycles of opening and closing so that we can look at the repeatability of the controllers in going from sash closed to sash open. We also look at the speed of response. So let's look at this in a little more detail. If we look at 2 examples, sash is closed. We have a fairly high minimum flow. We open the sash. We can see it's repeatable between sashes open and closed. There's good containment in each of these conditions. However, the bottom one shows as we open the sash, it starts off fairly low. It's overshooting and undershooting, and it's not been tuned properly to control the flow. Now you can imagine if the flow through the hood is varying, it's connected directly to the air supply. So what does the air supply have to do in order to keep it working in the proper balance? It's got to modulate as well. So these types of fluctuations are not conducive to hood containment, and they're not conducive to good VAV control. So something really important to look at is the operation of these VAV controls. Does it have adequate minimum flow? And is it stable? Those are the 2 questions we really want to know when we're testing the hood. If it's unstable or we don't have adequate minimum flow, those are going to cause problems, not only from the ability to conserve energy, but from a safety standpoint as well. So now we use this information from the fume hood. If we've tuned this properly and we've got proper response through the hood, it's connected to the controller that's controlling supply. So as I mentioned, if we're not proper on the hood, if it doesn't set up properly, it's not properly configured, that's going to cause air balance problems and other control issues, possibly with temperature control within that space. So the hood can drive the flow for a space, and we need to make sure that it is accurate and precise when we're doing our measurements so that we've tuned it properly to function over the range of operating modes. And so we have to look at this holistic system in order to achieve the objectives of safe, energy efficient, and productive spaces. Our balance here, total exhaust minus the supply equals the transfer air. So if exhaust is varying, our transfer air is going to vary. We're going to get problems with room pressurization. So if you're a hunter or you shoot darts or whatever, you're familiar with a target, and if we are not accurate or precise, we're all over the place. We can get good groupings, which means we're precise but not accurate. What we want to be is on the bullseye. We want to be accurate and precise. I can tell you we've done tens of thousands of hoods, VAV, and oftentimes we see significant errors. What we'd like to see is less than 5% error between the measured value and the reported value from the monitors and the building automation system. We also see that without proper testing and maintenance, VAV controls can degrade 30 to 50% within the first 5 years. Normally the fume hoods get tested and fixed, but the general exhaust and the supply are generally disregarded. And after 4 or 5 years, we got significant problems that create air balance issues and failure to meet the needs of the occupants. Now we move to the next section, which is the performance tests. When we look at performance tests, we're talking about airflow visualization first. We want to generate a visible smoke in the hood, and we want to be able to observe the airflow patterns. We're looking for reverse flow. Is it coming back out of the hood? We're looking at the vortex region in the top of the hood, and how quickly does that material clear out of the hood itself. Now this is qualitative because it's subjective. It's a person looking at these airflow patterns. Now there's other types of generators. In this case, we have a fog generator that was built especially for conducting fume hood tests. You put a generator inside the hood, a diffuser, and you generate the smoke, and you can dial in the quantity, and it'll continuously produce a visible plume of smoke. And then you can do things like opening and closing the sashes and use a mannequin to simulate a person doing walk-bys and so forth. And this allows you to identify weaknesses in hood performance. And we can see here, because of the aerodynamic design, there's actually escape out of the hood, and that would make sure, that would enable the person to be exposed to exactly what they're trying to protect against. Now, another thing is about the person standing in front of the hood. When a person walks in front of the hood, they affect the airflow patterns. And so when we're looking at this, we're generating our smoke with our fog generator, and we see that it's containing very well, but all of a sudden, here comes our mannequin or our person up to the hood. And when we see that occur, we see a dramatically different set of airflow patterns. So you may have said that hood performed properly when no one was standing in front of it, but clearly this video is showing that we've got some real containment problems, and that's the importance of testing it under as installed or as manufactured conditions. So again, removing the mannequin, we see that problem goes away. Working with the University of Toronto, they came up with a way to visualize airflow patterns using a series of lasers, creating a laser plane at the plane of the sash, allowed to look at the containment. And so we're looking at concentrations as they break the plane of the sash. The red is at the plane of the sash, and anytime it shows red, that means smoke is coming through that plane out of the hood. And so it's kind of an interesting test to visualize the airflow patterns in this way, and we learn a lot about the factors that influence hood containment. So next comes the quantitative test. We've evaluated it qualitatively with smoke, but now we want to quantitatively test the hood. Is it containing under a challenge where we use a mannequin to simulate a person standing in front of the hood? We generate a tracer gas in the hood. The ejector is placed 6 inches behind the plane of the sash. The mannequin is 3 inches outside of the plane of the sash. We generate our gas at 4 liters per minute, and we leave the mannequin in place for 5 minutes, taking a breathing zone sample every second. Now we move that mannequin from left, center, and right side of the hood, and we use the average 5-minute concentration as our control level. So for a as manufactured test, we generally accept 0.05 parts per million as an average in the breathing zone. For an as installed or as used test, we might allow it to go up to 0.1 parts per million. But that's a pretty low concentration. That's 10 parts per billion when we're looking at, 100 parts per billion from a containment criteria. So all of these factors have to be carefully installed and adjusted in order to achieve this level of performance. Now, oftentimes what we see when we're looking at tracer gas data in the breathing zone, this is on the left, we see some spikes. In the center, we may see some of the highest escape from the hood. And we look at this average over this period of time in order to get our average concentration. We also look at peak concentrations. So in this particular case, this hood would fail because it wasn't meeting the Z9.5 criteria of 0.1 parts per million for the ASHRAE 110 test. So you can't really say that it failed the ASHRAE 110 test. That's just a method of testing. What you can do is say it failed to meet the Z9.5 criteria for that test, or it failed to meet the owner's criteria, but ASHRAE 110 does not have a pass-fail. Now the next issue is, okay, we've measured the VAV response, we said it's stable, it's got the right minimum flow according to design, it's got the right face velocity, and everything appears to be operating correctly. But what happens if we put our mannequin in front, we do a Sash movement effect test? Again, monitoring slot velocity or flow, we can see the modulation and flow as we open and close the sashes. We're also monitoring cross drafts near the hood, and the red is tracer gas escape. So what we see here is when we close the sash, it overshoots and then comes back up, and then we open the sash and it overshoots and drops back down. And this variation in flow causes escape from the hood. And again, we see that repeated in the next subsequent opening, and we get a big escape. So by controlling this more effectively, we'll minimize that escape. So we can see here, we've got less overshoot and undershoot in the minimum and maximum, and we see no red, so we're not losing any containment, and so this hood is properly tuned to work effectively and protect the operator. Now, one of the things that we learned about SF6, sulfur hexafluoride, is that it was an excellent tracer gas for conducting hood tests. It's odorless, it's colorless, there's very few interfering agents, it's inert, it's very stable, and it's detectable at really low concentrations. The problem is it's expensive, and it's an extremely potent greenhouse gas. And so it's 24,000 times more potent than CO2 as a greenhouse gas. And as a result, it's being banned and discouraged in facilities all over the United States and all over the world. So ASHRAE sponsored a research project to come up with an alternative. And so we're working on that right now. The typical ASHRAE test, the sulfur hexafluoride, can cost you somewhere between $15 to as much as $50 per pound of gas. And it takes about a pound of gas to do a single ASHRAE 110 test. It also requires some very specialized equipment from detectors. You've got to have gas-tight leak fittings, leak-tight fittings. You've got to have a special regulator and stainless steel tubing and so forth in order to properly conduct tests. Very complicated test. What we found out during the ASHRAE project is that we could generate other materials. And in fact, we could use a material as simple as isopropyl alcohol. We could nebulize it and generate a plume that could simulate the SF6, and then we could use that as an alternative to SF6 testing. And the nice thing about isopropyl alcohol is it's also non-hazardous. It's a flammable material, but it's clean, it's green, it's less than 50% less than CO2 in a greenhouse gas emission, making it 48,000 times less potent than SF6. And as opposed to $15 per test, it's about $1.25 to use isopropyl alcohol. So we're investigating this for the next ASHRAE 110 standard, and then we'd use a photoionization detector to detect the concentrations escaping out of the hood. So this looks like a really potential challenge for replacing SF6. As I mentioned, SF6, the detectors are very complicated and expensive. This unit is the infrared, it's a spectrophotometer, and it runs about $30,000 to $40,000. Well, nobody's selling these now, and they're not supporting their use anymore, so that's become an antique. And then we have still the use on electron capture detector. They're about $30,000. Very finicky piece of equipment that requires an additional tracer gas plus a carrier gas in order for it to work. But we've found that those photoionization detectors are very inexpensive. They're about $3,000 each, have the sensitivity that's required to do the testing. They're much more stable and easier to use. So the combination of photoionization detectors plus the isopropyl alcohol gives us a good alternative. Well, we've done a lot of comparison tests with these different methods, and we've been able to identify that SF6 versus IPA give us similar results. So this is a fail condition. We have a marginal condition and then the pass condition. And so the IPA and SF6 are providing comparable results when we do the testing as prescribed by the method. So interestingly enough about IPA is that not only can you use it to measure hood containment, you can also use it to put the probes inside the hood and determine how low can you go before you get to a lower explosion limit on the hood. And then we can pull it into the laboratory and look at the air change rates. How effective are the air change rates at minimizing concentrations in the space? We want to make sure that the lab provides secondary containment. We want to make sure that it dilutes and removes contaminants. That's very important now during the COVID. And so we can test it. We can put a tracer gas in the lab and determine how effective is the lab at removing concentrations. And that test can be conducted not only in labs, but it can be conducted in offices and conference rooms and all kinds of different environments where people may be congregating, and we want to make sure that they're not going to be exposed to an aerosolized pathogen. So that comes to the Lab VEFF test. So we've tested the hood, we need to look at the lab. So in the lab environment, the lab is to support the hood. And so when we look at the overall flow, we need to make sure that in order for the hood to function properly, we've got to have the right air balance, the right room pressurization, the right supply, and it has to match the exhaust. And so they're working in tandem. So as the exhaust increases to the hood, the supply has to increase. As temperature changes, general exhaust is going to increase. All of these factors are associated and related. And so in order for it to work properly, we have to make sure the whole space is balanced. So we can conduct ventilation measurements. We can look at proper pressurization. We can confirm that the room is properly balanced and that the building automation system is reporting the same as we measured within some expected tolerance. And so this gives us the ability to do a more holistic evaluation. Now we also need to know what happens in the lab, as there could be concentrations generated outside of a hood. And so we need to be able to dilute and remove those materials. So typical generation rates, 0.1 to 10 liters per minute. How much airflow is required to protect people? So if we have a spill in the space and we have concentrations developing, let's say that we have a concentration on the bench, it starts to migrate out. The person standing next to that source is going to get the biggest dose. As it moves out to the space in a well-mixed scenario, it's going to occupy the entire space until the generation stops, and then it's going to begin to decay. Well, we know that that's assuming a well-mixed space, but many spaces are not well-mixed. Depending on where the diffuser is and the exhaust, it may be short-circuiting. We may not be getting the advantage of a well-mixed space. So our air change rate is just the flow divided by the volume of the room. It doesn't tell us how well the room is actually removing materials. It may be mixing them all up so that everyone's exposed and all surfaces are contaminated. Better would be to sweep the materials from the lab space. So how do we know that the air supply and the exhaust are working together to sweep the materials out? So we developed a test, again, using isopropyl alcohol. We divide the lab up into quadrants. We generate at the center, and we look at the migration of those materials to the different quadrants. And so we have our photoionization detectors arrayed around the room. We're generating our IPA. And we begin to see that from the point of generation, we can see the migration of materials into the space. Now, interestingly, this is not a well-mixed space because we're getting different concentrations and different durations depending on where we're located in that space. So if we took an overall aggregate for that space, the average of those readings, we could compare that to a theoretically calculated flow based on the air change rate. If the VEFF factor, which is the ratio between the actual concentrations to the theoretical concentrations, if it's greater than 1, that means the room is compromised. It's not working effectively. If it's less than 1, it's working well. So here's two examples. Two labs working at the same air change rate. The one on the left has a VEFF factor of 0.04. You can see the red here is the actual concentrations versus the black is theoretical. The dose is 174 theoretical, the actual is 8. On the right, same air change rate, 6 air changes per hour. The one on the left, the theoretical is 127, the actual is 547, a VEFF factor of 4.3. So which room would you rather work in? The one where it's removed, one that's circulating around and stagnating in the space. So I think you would choose the one on the left. Now we have the location of the supply diffusers. In this case, the supply diffuser is short-circuiting. It's also, not properly located, not going to get the performance out of this type of diffuser. Other circumstances where the diffuser is close to the hood or close to the exhaust, how effective is this going to be? We may be getting the right flow, but we're not using it to the advantage of conditioning or mixing in the space. So now, we've looked at the hood and the lab. Let's move up to the system. We anticipate that when we're opening and closing, that flow modulates through the hood. But in order to save energy, we have to reduce flow through the fans and through the air handlers. And so how well does the system track the changes in performance at the hood? Is it 1-to-1? Is it 100% sensitivity? Or is there some variation? So if we look at this and we're to plot it, if we looked at some plot over time, this is a week, Monday, Tuesday, Wednesday, Thursday, Friday, we see that the systems are in fact modulating to meet changes in demand in the spaces. So this would be a properly operating system. We can determine the minimum and maximum flow. I can't tell you how many buildings I've been to, and I ask them, what's the minimum flow when you're in unoccupied mode or all sashes are closed? And nobody knows. Who collects this data? How do we determine the min to max flow and what this averages over time so that we can verify that the system's operating properly within its expected operation? The accuracy and precision of the data matters. What we measure at the hoods, what we measure at the supply is critical because it's what's used to calibrate the controls. So our theoretical flow, whatever it was designed to be, should compare favorably to our actual, and that needs to then compare to the measured or reported values. How do we get those correlations? How do we make sure that they're all functioning properly, not only during commissioning, but subsequent, a year, 2 years, 5 years down the road? How do we maintain this correlation? One thing that we can do is test it. We expect that when the sashes are closed, we've got 7 hoods on the system. 1, 2, 3, 4, 5, 6, 7. They're all connected to a manifold exhaust. The supply is working in conjunction. So sash closed 200. We open the sash, we go to 1,000. The valve's programmed for 200 to 1,000. If we were to add that up from minimum to maximum for these hoods, we would see all sashes closed 1,400. We open all sashes 7,000. Our range of modulation would be 5,600 CFM. If this is a 50,000 CFM air handler, how likely is it to see an 800 CFM flow change at a hood? How do we modulate the flow and make sure that we're tracking it properly and that we're tuning these loops to make sure that it is in fact as sensitive as possible, but not overly sensitive that it's starting to hunt and seek? So a system operating mode test is what challenges this over the operation. So we measure the air handler flow, we record the VFD data, make sure that it's reporting properly to the building automation system, that we have the right metrics, and that we're using the proper techniques to measure and then calibrate the flow. Now, oftentimes we can see in this plot, this shows the difference between design, min, and max for different systems and different wings. And so we can see here a 30%, 28%, 21% modulation, but this system over here on the exhaust in the west wing, it's only 8% modulation. This tells us immediately that there's a problem with this area. It's not modulating to the degree that we would anticipate. And this building could go out of balance because it's not modulating in proportion to flow. So we have to take a top-down approach. We don't want to start testing the fume hoods until we know the exhaust fans are working properly. So looking at a top-down approach, we start with the system test first, then the lab, then the fume hoods. So there's a sequential path. And we have found that this will solve many problems and will reduce the time on site because we have a reduction in the duplicative work of test the hood, fix the fan, retest the hood, so forth and so on. So sorry, let me get back to sharing the screen. We've got, I don't know what just happened. Okay, sorry about that. So this top-down approach, moving from, okay, great. Moving from a top-down approach, we go from mechanical systems. Let me go back one. So if we know that the air handler exhaust fans are working properly, we can do a system operating mode test to challenge the systems, then follow it up with lab and then hood tests. And once we do this, we will save a lot of time and effort in optimizing the operation of the systems. So by doing this process, we can not only ensure energy savings, but we can reduce the operational costs, the cost to manage and maintain the systems by an additional 30%, just by changing the order of events. Why test a fume hood before you know the maintenance has been done on the fans? Just doesn't make sense. So this is a better ordering of events. Okay, that brings me to the completion there. Sorry about those problems. I'm ready and willing to take questions, and I can go here so that we can go ahead and field some questions.
Tom, you want me to feed those to you?
Sure, why not?
All righty. We've got about 5 or 6 of them here. We'll probably try to take care of these relatively quickly since we're a little bit over time. For a VAV system with a dedicated fan, what is your experience with fan speed response to limiting sash movement speed to avoid flow alarms?
Okay, can you repeat the question?
For a VAV system with a dedicated fan, what is your experience with fan speed response to limiting sash movement speed to avoid flow alarms?
Okay, that's a good question. So we're expecting, in order for the hood to contain, that the flow at the hood is going to modulate within 5 seconds from sash closed to sash open. But we're going to then translate that to the exhaust fans and expect the flow through the fan to modulate within 5 seconds from low to high? No way. That's, I mean, in order to get that correlation between the VAV flow response and the fan speed VFD response, that's a very difficult task. And so in our opinion, looking at that type of modulation for a single hood, single fan, or for even small manifold systems need to be scrutinized and look to see if that's the right technique for control. Why do you need a 5-second response? Why can't you, as you have the flow tracking, be more effective to ensure safety, but also that has to be matched with the exhaust fan. So it really need to look at what is our expectations of modulation, and are we able to actually achieve that modulation speed with all the different components on the system. So it's not something that there's a single answer to, it's really more of a systemic type of analysis that has to be done.
Got it. All right, next one, any update on the next version of standard 110 that you were allowed to talk about?
Yeah, sure. Well, the committee has been reformed, and we're in process right now of reviewing the different sections of the standard. One of the big areas, of course, is the potential replacement of SF6 with an alternative. Isopropyl alcohol is what ASHRAE, the research project, identified as a potential. We're under the process of investigating that right now. We actually, 3Flow, we did the testing and came up with that methodology, but that's just one source. We need to now replicate this to other organizations and have it tested in kind of a round robin type approach. So we're going to allow others to conduct the process and make sure that they get comparable data. So in terms of the time frame for this process, we expect to have some recommendations in 2021, and by the end of 2021, possibly early 2022, going to the full committee for review of a revised standard. So we're looking at updating the VAV response testing, looking at clarifying the airflow visualization, and the big one is really the replacement of tracer gas. So we hope 2021, 2022 to be in a position to promulgate a new standard.
Okay, great. Next one says more comment than a question. The velocity out of the exhaust fans should be significant. If this is the case, there should be no air down to the occupied level on the roof. And I guess you can comment
okay, well,
on
let me address that one because, you know, that's an interesting question. And when you look at the exhaust discharge, depending on the stack design, you could get a variety of different things happening. So you may have 2,000 or 3,000 feet per minute coming out of this stack. But look over here, you've got trees. So the airflow patterns over here may create turbulence, causing that flow to bend over towards the supply. You could have stack discharge effects. The stack itself could cause some issues. So there's a number of factors that are in addition to the velocity that we have to take into account. The velocity, 2,000-3,000 feet per minute sounds like a lot, but it's not in proportion to the airflow, which is measured in miles per hour. So we need to make sure that we've got adequate discharge height adequate dilution, and adequate discharge velocity to get the right plume. Okay.
Great, thank you. Someone asks, have you had occasion to slow a PID loop on an airflow damper actuator to create a test with less hunting by the damper to achieve set point, and has it produced favorable results?
Yes, absolutely. So we go through this process all the time. We test VAV response every single time we do a hood test. So in the initial commissioning, it gets tested, and then every year subsequently thereafter, it gets tested. And when we see these issues of hunting and seeking, we can go back in and look to see what are the predominant factors affecting that controller response. Maybe it's a bad location of the controller itself. It was put on an elbow, so how does it function properly if it's not properly located? And then there's the calibration itself. And then finally, the tuning, the PID loop tuning. Who does that? Is that the controls manufacturer that's putting it in? Is it during commissioning? Is it the tab responsibility? And so when we look at oftentimes the mechanisms that are used to measure and then tune it are not appropriate to get the adequate control. So we've had many opportunities to dial that in to maintain better containment. And so now we've developed both VAV response as well as flow stability requirements, not more than plus or minus 20% variation, will usually reduce the issues with containment problems if we can get that stabilized and controlled. And then from there, we can look at how well is the supply tracking. So then you do a trend and look at exhaust and supply as you are going up and down in flow.
Okay, I'm going to take two questions here that I think might follow nicely on each other. One person asked, do you know when ASHRAE will adopt the new tracer gas so that all agencies will be allowed to test with it?
Well, okay, so the committee has some work to do. We've got to verify that the data suggests by 3-flow measurement that it's a good alternative. But that's just us, right? So you've got to challenge the original author, and that has to be peer reviewed. So we've got to get some other companies to conduct these tests. So right now we're going to do a round robin testing. I'm writing the specification for the new generator. We're then going to give it to the hood manufacturers so that they can conduct some tests. And if it comes back after doing this round robin that they're getting similar results, well, then we know that we have a method that is repeatable. And so there'll be some other questions to ask. Is it a feasible method? Is the method of generation and the gas itself have any issues? So it's going to go through a process. It's likely to take a year and a half before we're ready to promulgate that. But I can tell you this, I'm so confident in the methodology that we're using it right now. We're going to test hoods with SF6 where necessary, but because of the strong global warming potential, we're going to encourage the acceptance of this method in advance. And it won't be the ASHRAE 110 method, but it'll be an equivalent method, we think. So we're pretty confident about it. But again, for its purposes of ASHRAE 110, that's probably a year and a half at least away.
Got it. So what I thought might be a decent follow-on question, where would someone start if they wanted to offer ASHRAE 110 fume hood testing services?
Well, that's a really good question. And let me flip back to okay, I'm going to show this diagram here. Well, first and foremost, if you want to do ASHRAE 110 testing, you want to offer it as a service, we've got to have all of the conditions to evaluate operational conditions. Every tab firm is going to be able to do this. Hood and lab inspections, phase velocity, cross-draft, VAV response. From here, the flow visualization, that's not a big deal. That's a fog generator or smoke tubes, smoke sticks. Again, that's a low-cost item. But it's the tracer gas containment test where you start getting this into the big expense and the complications. The meter itself, $30,000 to $40,000. The whole equipment apparatus, you've got to have a mannequin, the generator, the tanks, the regulators. You're into it about $50,000, $60,000 worth of equipment. And then there's the ongoing maintenance, calibration, procedures, training, and so forth to do it. Now, you can get into this business fairly simply and with some investment, be able to do it. The problem I have right now is that it's going to change. And when it changes, we're not quite sure. It could be 6 months, could be a year and a half, probably year and a half to 2 years away. So is that enough time to recoup the investment in the equipment to do ASHRAE 110 with SF6? There's also the impact on the environment. The more we generate SF6, it's a very strong global warming gas. And so we're putting a lot of it out in the environment. And do we want to do that during the interim? So I think transitioning to IPA or some alternative as soon as possible is the best method. But think about how do we ensure that the hoods function properly first? How do we get them to operate properly? If we can just do that, we will solve a lot of the problems. Use smoke tests in the interim to make sure that they contain properly. But I would, if I was starting out today and was going to do this service today, I would say, let's focus on getting the hoods operating properly. Let's focus on getting the VAVs operating properly. Let's focus on getting the exhaust and the air handlers working properly. If the systems operate properly, they're likely to provide the right level of performance. So that's the biggest hurdle right there, is getting everything to operate properly. I see that as a major opportunity in existing lab spaces to make sure that they function properly.
Got it.
I hope that helps.
Next question. The picture showed someone testing a hood with a velocity grid not on a ring stand. What say you? And if you want a little additional context, Tom, that question came from Galen.
Well, so I always anticipate the hard questions from Galen, so we would never recommend hand holding a probe to measure velocity, because velocity has turbulence, and turbulence is going to be that temporal variation in velocity. And if you are holding it and you're not steady, you're going to impart more velocity variance and more error into the measurement. So it's just prudent to mount that probe on a stand and measure the velocity so that you know that you're not affecting the velocity measurement by the actions of the tester. You've removed the tester from the equation. And then if you're measuring turbulence, it's because of room air turbulence or exhaust air turbulence, or the VAV is not tuned properly. So we try to eliminate variables. So we would never advocate using a handheld measurement for phase velocities or for VAV response, just because we want to minimize errors. We don't want to impart those in the measurement. Now, if you're just doing a quick check to see if you're in the ballpark, okay, that's fine. But if you're certifying a hood, our integrity is often in parallel to our accuracy and the precision of our data. So if we can't collect accurate and precise data, it affects our integrity. And so we want to be sure that as we're measuring, that we can walk away with a high degree of confidence that we've collected good data, defensible data, and if somebody comes in behind us, I don't want it to be questioned because we did the method improperly. So that's my answer to Galen's question. Minimize the turbulence, minimize the errors. Putting it on a stand is the best way to do it.
Great, thank you, Tom. Next question, for commissioning purposes, is there any specific credential that needs to be presented in the test report by the manufacturer, third party, or commissioning agent?
Well, okay, so right now there's no qualifications that are required to do hood tests. Anybody can go out and do it, put a sticker on a hood. I think that is a definite weakness. There is a NEB certification, you guys know them. There is now a CETA certification, the Controlled Environment Testing Association has a test, but none of them really are required or nationally mandated as an ANSI standard or as a requirement that holds a lot of weight at this point. I think it's an opportunity for AABC to be the purveyor of this kind of standardized process. When you want people balancing, you expect that they have certain qualifications. To test a fume hood, we'd expect similar type of confidence in their qualifications. And so certainly experience is a big factor, their ability and competence to use the equipment, their ability to analyze the data and to make good recommendations on how to correct problems. Those are all, attributes and requirements of those conducting the test. But as far as an actual qualification, we're in need. We do not have that right now. So it's something that really needs to be specified by the owners and adopted by the national organizations as a way to support this.
Got it. What type of airflow instruments should be used to calibrate phase velocity?
Well, right now, the best instrument that we are aware of is a hot wire anemometer that's connected to a transducer so that we can get real-time velocity measurements. And we mount the probe at the grid traverse, and then we take readings for no less than 10 readings per location. So we're reading every second for 10 seconds. And what we did is we analyzed the data statistically and found out that by fixing the probe on a stand, taking at least 10 readings per location, you get a high degree of confidence that you're measuring the right velocity through the opening. But that may not translate to the total flow in the duct. That's just the velocity through the opening area that we've measured. There may be other leakage behind the sash, behind, through the opening, the bypass, and other areas, that the total flow through the hood may be significantly more than what we're calculating by Q equals VA. So the velocity times that area of the opening might result in less flow than what we measure in the duct. So it's very imperative that we do both. We need a pitot traverse on the exhaust to get the total flow, and we need a face velocity to ensure we have the right speed of air entering the hood. And so the best equipment, in my opinion, right now is a velocity anemometer, but the Velgrid or a short ridge type of thing is not appropriate. It just does not have the accuracy at low velocities, and it's susceptible to pitch and yaw or the angle of incidence of the velocity. And we've got the data to prove it. It's a good measurement for just spot checking, but not for certification.
Okay, and you just successfully answered somebody that asked a similar question and touched on things like Belgrid and whatnot. Just a quick note, Tom. Galen followed up noting that he has talked about in a few recent meetings that AABC is planning to add a standardized test for the 110 in an upcoming standard. Just
well, great. That would be
discussion.
Very helpful, a very benefit to the society.
Couple more. Do you have recommended safe distance between the outside air intake and the point of exhaust?
Okay. Well, that's a complicated question. So generally we'd say just offhand 30 feet. But why? It's hard to say. You could actually put the intake at the bottom of the stacks if they were properly discharging, and then the airflow would be carried away from it. And so you'd have less likelihood of intake. But that is a complicated question based on the height of the building, the configuration of the building, the topography of the space around it, the impact of other buildings on the airflow patterns, the typical direction of wind, the wind speed. So I leave those questions up to the experts that do that type of wind wake modeling and the actual CFD for building dynamics. So I'm not sure I can answer the question, what is a safe distance? When I look at them and I say, gosh, they're less than 30 feet, that gives me a pause. It makes me go up there and go, oh boy, we may have some issues, but I can't guarantee it unless we do some testing. So I have some rules of thumb. I'll say that's an indicator of risk, but it's not necessarily a hard fail and say, well, gosh, it's too close, that's going to fail. It's really complicated.
Okay, thank you. Have you experienced any issues with IPA or any other chemical affecting the sensors that monitor for spill?
Oh, such as like a chemical sensing system like air acuity or something like that in the lab, a demand control ventilation. Well, interestingly, the sensors themselves that would do that detection are the same type of photoionization detectors, or there are other types of semiconductor type chips. IPA, usually in the concentrations we're using, is very, very low. We've not seen any impact on those type of sensors. However, use of IPA to verify and validate the operation of the air acuity system is a good one. You put a sensor on the wall or in the general exhaust duct that it's going to detect a spill. Well, how do you know that it does it? How do you know that it actually detects it with sensitivity and then modulates the flow accordingly? Well, we've got to challenge it. So put a little IPA out in the room. Open up a beaker of IPA and see what happens. Does it detect it? Right? So I think right now there's a lot of trust in these systems to modulate, detect, and modulate flow with not a single standardized challenge test to run right now. They get put in, nobody tests them. Right? So nobody's validating that they're working. And we're putting people's health and safety at risk by not adequately testing these systems. And that's an opportunity for the balancer, in my opinion. Go in there, make sure you challenge it, that it detects it, it modulates the flow as we expect it to, and that it translates all the way up to the air handlers and exhaust fans. Great opportunity, in my opinion.
Okay. Tom, I've got two more questions, and I think then we're gonna call it at that. First one, I apologize, is one I missed from early on. Somebody just simply asked, I said they missed what was wrong with the fan inlet elbow in the short stack slide from earlier in your presentation, if that's easy.
Okay. Great question. So I'm going to go ahead and show it again, just so that we have no vagaries on that answer. Let me get the right slide here, of course. Well, let's take a look at this entry. Can you see that on the screen?
I can see the image, yeah.
Okay, so here it is. The airflow is coming out of the building, and it's going to be expected to do a 90-degree turn directly into the fan. How many straight lengths of duct should you have before the fan inlet? Right? What is the likelihood that you're getting a rotation of flow that's conducive to the fan operation? This square edge, I will guarantee there's no turning vanes in here. And so we know that this fan is probably going to lose about 20 to 30% of its efficiency because of the inlet connection not being appropriate and not getting good flow into this fan. So that's an inefficient inlet that's going to cause poor performance of the fan, which is going to require more energy in order to achieve the desired flow rate. And that's what I meant by an improper duct inlet.
Got it. All right, and then last question. Would you recommend isoamyl acetate for checking re-entrainment? Is there a guide someone could go and look for a guide to check this concern?
Okay, so isoamyl acetate is, banana oil. And so banana oil has a high, a very, very low detectable limit through your nose. Your nose turns out to be a great sensor until it gets oversensed and you get into olfactory fatigue. So banana oil or isoamyl acetate can be measured with PIDs. It's nice that it has an odor that you can detect with your nose. So if you wanted to run a quick test to see if you're getting concentrations at the air intake, sure, you could generate some isoamyl acetate in the hood and see if you can smell it. That's not a bad way to do a quick and dirty type of test. You could also do it in a lab space or in an office or in a conference room. If you wanted to see if somebody sitting across from you at the conference table, if you were going to inhale their effluent or their pathogens emitted by breathing, well, open up a little isoamyl acetate. If you can smell it, you're screwed kind of thing. But, it shows you the airflow patterns. And so isoamyl acetate, it's been used to test respirators for decades. So no problem with its use. Be careful with it though, because it does have some hazardous properties.
All right. Tom, thank you so much. Thank you for staying on for some extra time to answer a lot of really excellent questions. And again, we do thank all of the attendees. We had actually nearly 250 people in attendance. So thank you all for being here. Thank you for your excellent questions. Really helped improve everything. And we hope to see all of you tomorrow for the next webinar presentation, the COVID-related panel on ventilation. And one note that, again, you will get your continuing education certificates in just about a week after completion of each session. So thank you very much. And again, everybody stay safe. And thank you for being here. And we're going to play you out with an AABC video. Thank you, Tom.
Thank you very much. Appreciate AABC and the opportunity. Thanks, everyone.
Thank you, Tom.
The Associated Air Balance Council, the world's oldest and most respected association of certified, independent test, adjust, and balance agencies. AABC offers its members and the industry technical education and training, an ANSI-approved TAB standard, and a variety of resources with the goal of ensuring that systems are tested properly and operate as designed and intended. Let's take a look at why independent test and balance is important and why AABC certified agencies are the service providers of choice for every building owner and design professional.
The testing, adjusting, and balancing process is a benefit in many different ways to the owner. You know, that not having the process done may save some dollars on the front end, but the process in itself is all to make sure that the owner receives what he paid for.
For my customers who are either building owners or operators, independence matters because they're getting an unbiased view at their mechanical install, at the design, and actual end performance of the equipment that they're having tested and balanced.
Well, they just get a better product. They get somebody who's looking at all the pieces and how they all tend to work together.
For me, independence is more about trust than it is anything else. Knowing that when they come into the room with a problem and they've got an independent entity as a tab agent and they know it's independent because they're certified by AABC is the most important part to the process.
They're high quality, high caliber people who are extremely driven to make high energy efficiency buildings and make an impact on what really is the demand of the future, which is the energy market, and how do we make sustainable buildings. And I haven't seen a group of people at any of the other organizations that have that knowledge base that AABC brings to the table.